Today we'll have a discussion about how to solve logarithmic equations, but the discussion about solving logarithmic equations will actually go back to a discussion about solving exponential equations. Back in Unit 9, we learned about solving exponential equations. We really only had one choice, but now that we've studied logs as the inverse of the exponential function, we're going to have a second choice for solving those exponential equations, and sometimes it'll be the only choice that we'll be able to use. A reminder of a few things we've already seen. First of all, on the left side of the screen, when your base of your logarithm and your argument match, your answer is always a 1. Here we've got a common log base 10 of 10 is equal to 1, log base 3 of 3 is equal to 1, and the natural log of e is equal to 1. Remember that a natural log has a base of e. So we're matching the bases and matching the arguments. Let's just turn one of those around and see how that happens. I am taking this expression and saying that that's equal to some unknown quantity x, and then I go into exponential form. I turn into 10 to the x is equal to 10 to the first. That tells me that x equals 1. The same thing will happen on all three of these cases. Something else you want to notice on the right hand side of the screen, if you were ever using your log buttons on the calculator and the calculator gives you an error, it is most probably due to your trying to take the log of a negative x. If you look at the picture of the log function, or you look at the picture of the natural log function of x, you can see that neither one of these functions exist for any x that is 0 or less. They don't exist on the entire left side of the graph. So if you try to put a negative number in for that argument, it's going to say it's an error. It doesn't. The value you tried to put in is not in the domain. Okay, in Unit 9, as we talked about, we solved exponential equations. We would look at something like 9 to the x equals 14, and we would be attempting to get the same bases on both sides of the problem. Well, I cannot write 14 as 9 to some power, so I would start going lower. I know I could turn 9 into 3 squared. But when I get to the other side, that still doesn't help me with the 14 because I can't turn 14 into 3 to any power. So I really am kind of at a loss as to how I'm going to solve this thing. That's where the logs come in handy, because in solving an equation, if I do the same thing to both sides of the equation, and I'm going to take the log, the common log of the left-hand side, I'm going to take the common log of the right-hand side. As long as I've done the same thing to both sides of that equation, I haven't violated any rules of algebra. And now we'll take this exponent here and we'll swish it down in front using the laws for expansion and contraction that we learned about. Now it says x log of 9 is equal to log of 14. And the last thing we need to do in order to get that x by itself is divide both sides by log of 9. And so we end up with x equals, and now we have a quantity that we can get from the calculator. So we'll grab our calculator screen and we'll type in, use our fraction template, control log, get out of that base because we can't change it. We'll put a 14 up top. Down the bottom again, control log, and we'll get out of the base, put a 9 into the argument, hit the enter key, and we get this number, which I'm going to write down. It's 1.20109. And we would round according to the instructions. Well, we can use a common log, log base 10. Let's see what happens if we use a natural log instead. I'm going to put ln of 9 to the x on this side, and we'll take the natural log of 14 on the right-hand side. Again, I'm going to use my laws of exponents. Remember, they apply the same to common logs as to natural logs. So this becomes x natural log of 9 is equal to natural log of 14. And the last thing to do here to get x by itself is divide both sides by the natural log of 9. Again, it's time to pick up our calculator because we've got x equals on the left and it's just a number on the right. So in the calculator we can type now fraction template and find the natural log of 14 on the top and choose the natural log of 14 of 9 on the bottom, and I have the exact same result as the last time, 1.20109. So that should prove to you that it doesn't matter which one you use as long as you do this both on the same on both sides. And again, round off some rounding instructions. One tip that you might want to use, it's a little bit easier for you to use the natural log function in your calculator just because you don't have to jump out of that base that you're not allowed to use. So that's up to you. I will make this suggestion. When you are solving and you see an E already existing in the problem, you might want to consider natural logs. If you see a 10 already existing somewhere in the problem, you might want to consider common logs. And you'll see why with this next example. In this next example, you see an E appearing in the equation. So that's something where I would immediately want to think about using natural logs. But in this particular problem here, we have this exponential term. It's not by itself. There's a 6 in front of it. If you recall, when we were solving exponential equations, we would get rid of coefficients, or we would get anything that's being added or subtracted before we got busy working on the exponential term. We'll do the same thing here. In this problem, I'm going to begin by dividing both sides by 6 in order to get rid of that coefficient. And that leaves me with e to the negative x power is equal to 1/2. Now I'm ready to use my logarithms, but I'm going to choose a natural log here because I see the e base. So we'll take the natural log of both sides. I'm going to swoosh that negative x down to the front. And what I'm left with is negative x is my coefficient times the natural log of e. But if you recall on slide 1, we said the natural log of e was equal to 1. So it's going to help us clean that term up a whole lot faster. On the other side, I still have the natural log of 1/2. I'm ready to, well, not quite pick up my calculator. Let's not forget the fact that we have a minus out front here. So then I'm going to write x is equal to minus the natural log of 1/2. And at this point, it would be time to pick up my calculator. So we'll do, and I will actually type in that minus sign first, I think, so I don't forget it. So minus the natural log of, you can use your fraction template, 1/2. You can type in a 0.52. And we'll get a 0.693147. That's a positive answer. 0.693147. We'd be rounding according to the instructions. I'm going to go back and look at that graph for just a minute, and this result may surprise you that it's positive. Well, don't forget we negated the natural log of 1/2. If we take a look at our log functions, we see that they both go through the point 1, 0, which means any x that's greater than 1 would give us a result above the x-axis or a positive value, and any result that's in between 0 and 1 would give us a negative value, something below the x-axis. So if I see a log function and I have an argument that's less than 1, that particular part of it will give you a negative result. In this problem, we ended up turning that negative result around because of the other minus sign we brought over. Okay, well, what that means is all those problems, all those application problems that we had to use graphic solutions for in the last unit, we now have an algebraic method. We didn't have one back then, so you were forced to put that horizontal line on the graph that gave you your value. In this case, we're talking about population reaching 15,000, so we made that red horizontal line at 15,000 on our vertical axis, and we plotted our exponential function in the blue curve that you see, and then we'd have to find the intersection point. Once we found the intersection point, we knew what our solution was. We knew that the time measured in years here would be 5.96 years. Well, now we can take that same equation and we can solve it exponentially. When I have a final value of 15,000, I'm filling 15,000 equals 8,500 1.1 to the t power, and now we can use what we know about logs to be able to solve for t, and it's fairly quick, and I think most of you would agree that it's a simpler solution than a graphic solution. There's actually less work to do here. Again, I want to start out by getting rid of that 8,500 just to make my life easier. So I divide it out on the right hand side, and then I'm ready to take the log of both sides. I'll choose to use a natural log here. Cross off those zeros. I've got 150 over 85. You can reduce that whenever you want to reduce it, but you can put it in your calculator as is. Equals, well, when I take the natural log of this side, that means the exponent of t is going to come down front. So it's t times the natural log of 1.1. Last thing to do, we're almost at our we're almost at our algebraic solution here. If I divide both sides by the natural log of 1.1, that will leave me, oops, it's a 1.1, that will leave me with nothing but a t on that right hand side, and then I can move over to the left hand side and type all that into my calculator. So we'll do that. Bring up a fraction template. On top we've got the natural log, and now another fraction template inside the argument. I'm going to put a 150 on top, and I'll put an 85 on the bottom. That's all in the argument of the top log. Let's jump down to the bottom of my original fraction, and in the bottom I'm going to bring up another natural log, and this one is just a 1.1. And I get a 5.953 95932. Let's see how good that is. 5.95932, because we solved this problem graphically before we started, and when we solved it graphically we got 5.96, and now we're coming up with a 5.959, so pretty darn close. And you'd round off. This one said according to the nearest year, so in either case would be rounding off to 6 years. Just some tips. You have a number of word problems for tonight. You just saw an example of exponential growth. If you look at that graph, that value is growing. And this was a periodic growth, not a continuous growth. So I need to remind you that if it's periodic, in other words, we're going to say, well, we have a rate every quarter, or we're going to compound every quarter, it's going to grow every quarter, it's going to decay every quarter, versus continuously growing or continuously compounding or continuously decaying, a constant rate of growth, a constant rate of decay. These are all things that are associated with our shampoo formula down here. And a lot of times you're given the formula, but just verify. If you have to come up with your own, we're going to start off using this one. If we've got if we're measuring this in terms of units, make sure if you're using this top formula that whatever units you're compounding in, if you're compounding in days, then this rate has to be in days. If you're compounding in years, that rate has to be in years. You don't have to worry so much about that with this one, because your rate and your time, well, still your rate and your time should be matching. And the last tip I want to give you for these word problems, you will see things like at least 4,000. When you say at least 4,000, that means you have something that is greater than or equal to 4,000. Numbers are at least 4,000 or 4,000, 4,005, 4,010. And if you have to turn that around in an equation, because a lot of times when it says at least 4,000, we're actually given the ending number there, the final amount, or in this case the final amount. And so when you turn this around, if you were to put the 400 on the left and the other expression on the right, then you always keep the arrow here pointing to what it was pointing to. So we might be setting those up as 4,000 is less than or equal to, and we've got our equation for compounding over here. And you'll interpret your answer appropriately.